Hey folks, Tom McNamara here again for our course in trigonometry. In this video I wanted to talk about the idea of radian measure for angles. Okay, so up to this point in our course we have discussed angles using degrees to measure the angle. So a 360-degree angle corresponds to a full rotation ending up back where you start. The radian system, I would kind of make an analogy to measuring in the customary system that we use in the US versus the metric system. Okay, so there are two ways to think about, let's say, my height. You can say I'm 71 inches tall or about 180 centimeters tall. Okay, so those two measurements, they convey the same length using the two different systems. And we have two different systems for measuring angles. There are certain advantages to using this radian measure that we will discuss in this video and also later in the course. In particular, the advantages come in that they simplify certain geometric formulas. Let me give you an example here. We'll talk about a bridge to the idea of radian measure. Let's talk about arc length. Okay, so we're going to take a circle here. It's not a bad, okay, it's okay. I'm going to imagine a circle. Let's say the radius of my circle is 5. Okay, r equals 5. And let's say I had a 120-degree angle. Now, if I was asking what is the length of the arc that is cut off by this angle, I'm asking about this right here. Okay, can you see that I'm highlighting it in blue right there? What is this length? So let's think about how we can answer that with what we know right now. Well, I know a formula for the circumference of a circle, the distance completely around the circle. The entire circumference of the circle would be 2 pi r. All right, so since I know the radius, my circumference is 10 pi. Now, I haven't gone the full way around. If I'm going from here to here, making a 120-degree angle, that's only 1/3 of the way. How do I know it's 1/3 of the way? Well, my arc length is going to be the proportion of the full 360 that I've gone. In this case, 120 over 360. So that's where I'm getting the 1/3 from. So 10 pi over 3. Okay, so I had a 120-degree angle. I get this right here. Now, I'm actually going to encourage you to kind of think about it this way. Okay, 2 pi over 3 times 5. I'll show you why in a second. Let's look at another arc length problem. Okay, so let me keep that there. I'll imagine the same circle, still radius 5. Let's tackle maybe like a 60-degree angle. Okay, a 60-degree angle. Let's talk about that arc length. So in other words, I'm talking about this distance right here. Try my best to highlight it in blue. Okay, so that's, what is that length? Okay, we'll call that S. Okay, S for, comes from the Latin word for distance. All right, so we'll do the same thing here. I'll take 2 pi r. Now r I know is 5, okay, now 2 pi r is coming from the circumference of the circle. And then I take a proportion. How much of the full 360-degree revolution have I done? Okay, so this would be 60 over 360 degrees. So this is 1/6. Okay, so pi over 3 times 5. So basically what radian measure is doing is saying, okay, instead of doing this proportion here and then multiplying by the 2 pi, let's just make that angle, let's just call that angle pi over 3. Okay, so if we measure theta in radians, and I'll show you how to convert from degrees to radians straight away in just a second. If we measure theta in radians, the length of an arc is equal to the radius of the circle times the angle theta. And we'll see this also simplifies some area formulas and some other things. So there are definite advantages to working in radians. This arc length formula getting simplified is one of them. Okay, so if we measure theta in radians, the arc length is equal to the radius of the circle times the angle. Okay, now let's think about how we get from this degree measure to radians. Okay, so an angle of 60 degrees corresponds to pi over 3 radians. Here's the quick conversion formula. If you take your degree measure, multiply by pi, and divide by 180, that gets you your radian measure. Okay, take your degree measure times pi, divide by 180, that's your radian measure. Conversely, if you have an angle measured in radians and want to go back to degrees, well, you multiply by 180 and then divide by pi. Okay, so we have this little fraction giving us a way to convert one to the other. Basically, 2 pi radians equals 360 degrees, right? So 2 pi is kind of the 2 pi r the full way around the circle, 360 the full way around the circle. So that's where this is coming from, okay? 2 pi to 360 simplifies to pi over 180. Let me do a couple quick examples of dealing with these radians. Okay, so let's start with one that looks like this. Let's just do a straight conversion here. Let's convert 430 degree, let's start with this one. Convert 50 degrees to radians. All right, so we're using this formula right here. We take our degrees times pi, divide by 180. All right, now let me see what's in here. There's definitely a factor of 10. that I can cancel, so this is 5 pi over 18 radians. I don't think it can be simplified any further. Okay, one more. Convert 7 pi over 3 to degrees. Okay, convert 7 pi over 3 to degrees. So I take my radian measure, and I multiply by 180, divide by pi. Okay, the pi's cancel. There's a factor of 3 in 180. 180 is 3 times 60. Okay, so this is 420 degrees. All right, I'm going to ask you to be very conscientious about using that degree symbol. Okay, because if I see an angle that doesn't have the degree symbol, I'm going to assume you mean radians. If you want to let me know you're talking about degrees, use that. Okay, so we can go back and forth. We can take something in degrees, change it to radians. We can take something in radians and go to degrees. Let's do a few computations of trig functions when we're dealing with radians. How about we try this one? How about we find, I don't know, cosine pi over 4. Now, as you start to work with these, you'll recognize certain important values, but remember your special angles. Okay, 30 degrees, well, if you multiply by pi, divide by 180, you get pi over 6 radians. If I got 45 degrees, okay, well, 4 times 45 is 180. Okay, double 45 you get 90, double 90 you get 180. So 4 times 45 is 180. So 45 degrees is pi over 4 radians. And we saw this one when we were dealing with the arc length. Okay, so our special angles in degrees, 30, 45, 60. In radians, pi over 6, pi over 4, pi over 3. So if I'm talking about finding cosine pi over 4, and I guess I can just use the special triangle directly. So cosine 45 degrees, opposite over hypotenuse 1 over radical 2, or if you like to rationalize your denominator, square root 2 over 2. Let's try another one. Sine 2 pi over 3. Okay, well, 60 degrees corresponds to pi over 3. 2 pi over 3 would correspond to 120. Right, just hit both sides of this equality here with a 2. Okay, so if we're talking about an angle of 2 pi over 3, we're going into the second quadrant. So 2 pi over 3, reference angle of pi over 3. Making this my reference triangle. Okay, pi over 3, we're remembering that 60 degrees right there. That must mean this is 30 degrees or pi over 6 radians. Okay, so sine 2 pi over 3 is root 3 over 2. Okay, so when you go through the practice problems for this section, I'll assign you some practice problems in WebAssign. I want you to get good at converting between degrees and radians. I want you to get so good that you don't have to go to degrees every single time. Okay, recognize the special angles in radians. And number 2, be able to state angles and reference angles in both systems. Okay, so this is 2 pi over 3 radians, reference angle pi over 3. Okay, so this is 0 radians, this is pi over 2 radians, this is pi radians, this is 3 pi over 2 radians. Okay, we can get all those using the conversion formula. Practice those special angles until you have them down, and you can just recognize them. And be able to evaluate the trig functions, not just for degrees, but also for radians. Okay, we're going to start to transition to using that radian system throughout the course, and we'll see it actually does have a lot of advantages, simplifying some of the formulas we're going to work with.